In this video, we're going to discuss the details of DFT and how we find the irrelevant equations. And we're going to start by considering what are known as the Kohn-Sham equations. These are the practical equations that allow you to do a DFT calculation. So the problem, as we've seen, is to minimize the ground state energy with respect to the charge density while maintaining the total number of electrons. So we want to minimize EGS with respect to, that's WRT, rho of R, subject to the total number n being equal to the integral rho of R dr. And in the usual way, we will use the details of functionals and Lagrange multipliers to do that. So at the ground state, to linear order in delta rho, we can say that delta E ground state minus mu delta n should equal 0. And we can define that as being equal to the integral dr of v of r minus mu plus delta t by delta rho of r, that's a functional derivative, and again there are some notes on that in the notes, in the appendix, plus delta g by delta rho of r, delta rho of r. And we have defined g of rho of r as simply equal to E Hartree plus EXC. So those are the electron-electron interaction energies. The only way that this condition can be obeyed for all values of delta rho is if the following equation is true. So delta T by delta rho of R plus V of R, the external potential, plus delta G by delta rho of R is equal to mu. Now, a little side note, note that for a non-interacting electrons, we would have G is equal to 0. So the condition would be, in this case, delta T by delta rho of R plus V of R is equal to mu. That should look familiar from the Thomas Fermi work that we did in the previous lectures. So let's come back to our interacting picture and let's define an effective potential. So we're going to define V effective of R is equal to capital V of R plus delta G by delta rho of R. And in this case, if we then put that in, we find that our equation from above becomes delta T by delta rho of R plus V effective of R is equal to mu. Now, this means that the ground state for interacting electrons with a potential V of R is the same as the ground state for non-interacting electrons with the potential V effective. Whoops, lost an I there. This is exactly the same principle that we saw for Thomas Fermi theory. And the reason this is important, and in fact the reason that we defined the kinetic energy T as being the kinetic energy for non-interacting electrons, is because we know how to find the ground state for non-interacting electrons. What we do is the following. We solve the equations, the simple Schrödinger equations, as follows. You have minus h bar squared over 2m del squared plus V effective of R, I'll just correct that, sorry. V effective of R psi n of R is equal to epsilon n psi n of R. And then we create the charge density rho of r is equal to twice the sum over I is equal to 1 to n over 2 of the square modulus of psi I of r squared. Now, we haven't yet touched on the exchange correlation. So we're going to just look at the simplest possible approximation there, and this is known as the local density approximation, which is also goes by the initials LDA. And the LDA follows very much in the principles of Thomas Fermi theory. So what we can say is the exact form of EXC of rho of r is unknown. That's true even 60 years on from the beginnings of DFT. However, it can be calculated very accurately for a uniform electron gas using techniques such as quantum Monte Carlo. I'm not going to finish writing using techniques, that's just too much. It can be calculated very accurately, still approximate, but it's almost exact for using things such as quantum Monte Carlo. And what we're going to do is we're going to calculate, or we're going to assume that we're going to use the same kinds of ideas as we had before. So we're going to say that we want to have epsilon xc, which is the energy density per electron. So it's the exchange correlation per electron in the uniform electron gas of density rho. If we do that, then we can define EXC, the total exchange correlation energy for our system, as the integral dr of epsilon xc of rho of r multiplied by rho of r. So we then have that first term, which is the energy per electron, multiplied by the electron density per unit volume, giving us an overall energy per unit volume, which we then integrate over the system to get the total energy. In a later lecture, we'll discuss some of the other possible approximations for the exchange correlation energy, and also which approximations are reliable. It should be noted that the LDA is very crude, and yet has actually been quite successful. So now let's consider the final missing piece, which is the Kohn-Sham potential. So that's the effective potential that we see in the Kohn-Sham equations. We want to know what delta G by delta rho of r is. And of course it's just equal to delta E Hartree by delta rho of r plus delta EXC by delta rho of r. The first term, delta E Hartree, is rather easy. It's just the standard classical electrostatic potential, V Hartree of r, and that's given by E squared over 4 pi epsilon naught integral dr rho of r over, sorry, that should be a dr prime, over r minus r prime. The exchange correlation energy, delta EXC, will depend on what functional you are using for the exchange correlation. For the LDA, it can be defined as follows. It's d by d rho of rho of r epsilon xc of rho of r. And then, depending on the form of that term EXC of rho of r, the derivative will change. But overall, we can define that as being the potential VXC of r. So overall, the total effective potential that the electrons experience is written as V of r, that is the external potential from the nuclei, plus V Hartree of r, plus Vxc of r. So we now have a complete set of equations and approaches needed. So in a standard DFT calculation, we will follow the following procedure. As we saw with Thomas Fermi theory, there's a problem of self-consistency. So the potential that you need in order to do the calculation depends on the charge density. So we have to choose an input density. Typically this is done as a superposition of atomic densities or a charge density from a previous calculation. That input density gives us V Hartree and Vxc. So we can then solve the Kohn-Sham equations, which will give us the eigenstates and the eigenvalues, psi n of r and epsilon n. We then build what's called the output density. So that's the density using psi n, so the Kohn-Sham equations. So rho of r is equal to the sum of psi n of r squared. There then follows a rather difficult and non-linear procedure, so we iterate to what is known as self-consistency. If you do the naive approach of just putting the output charge density in as the input charge density, you will often find that things are extremely unstable. So there has been a lot of development work on this whole problem. Because it's a nonlinear problem, there is no single solution which allows you to guarantee that you will get to the ground state, and there are well-known examples of systems that are very difficult to converge. Nevertheless, in most cases we can now get to a ground state, and once you've got a charge density which is equivalent to, which is consistent with the potentials V Hartree and Vxc, you can then calculate the total energy. You can also calculate forces on the atoms, the stress on the unit cell, and do a variety of other analyses. So that finishes the description of the basics of density functional theory. I would urge you to read the notes which go into more detail and provide extra pieces of information.